We have been building manned aircraft at Convair for more than 40 years. They have been great aircraft, safely and reliably doing the job for which they were designed. Several thousand are in service today. On the Lunar Excursion Module, we intend to produce the most reliable manned flight vehicle ever built. We welcome the opportunity to work under the direction of the National Aeronautics and Space Administration in this vitally important program. The safety of the crew and the success of the lunar mission will be paramount in our design and development thinking. Our goal will be to achieve this reliability by thorough development testing, proving step by step that the module will meet the requirements for crew safety and mission success. Personnel selected for LEM will be identified by this special badge. Each worker's name will be recorded with the task he accomplishes, thus identifying him openly with the quality of his work. All materials, components, and systems for LEM will be carefully selected, and those meeting the program standard will be identified with this seal. To ensure adequate attention to both LEM and Little Joe 2, one of the most highly qualified engineers in General Dynamics, Mr. E.R. Peterson, has been selected as Vice President and General Manager of all NASA programs at Convair. In direct charge of the LEM team will be a veteran engineer and program manager, John Bergstrom.
Our LEM organization will be a strong Apollo project within Convair. It will be devoted to the lunar program without interference of existing or future contracts. We will be supported in our design and development efforts by the total resources of the General Dynamics Corporation. The knowledge and skills of the various divisions will be channeled as needed into the LEM project organization, reporting to one authority at General Dynamics Convair in San Diego, California. Here, the Lunar Excursion Module project will have full authority for all phases of the vehicle's development testing under the technical direction of the National Aeronautics and Space Administration. In and near San Diego, we have well-equipped assembly and test facilities, modern tooling, and extensive research laboratories. Since we're now completing our jet transport program, the equipment and facilities are immediately available for the Lunar Excursion Module without the interference of other major programs. We plan to conduct major LEM tests, from static firings to tethered flights in the state of New Mexico, where we've been engaged in aircraft and rocket testing for the past 14 years. We have personnel and facilities in New Mexico now, and we've been active there since we flight tested the forerunner of today's ICBMs in 1948. We plan to conduct final assembly and checkout of the lunar module at White Sands, where we'll also conduct propulsion and system tests. Remote test areas and available facilities are among the obvious advantages of New Mexico, but of chief importance is that key lunar project tests with Apollo and Little Joe 2 will also occur here. My assistant program manager was Convair's Chief of Engineering Flight Test. He is a veteran test pilot who has flown all types of experimental aircraft, including the XP-46. He is Phil Prophet.
Our history is one of aerospace pioneering, and from this history have come hard-won lessons and experience that bear directly on LEM. Through aircraft development, we're thoroughly familiar with the problems associated with placing a man in the loop of a high-performance, highly sophisticated flight system. The problems encountered and overcome with aircraft are similar in many respects to the design challenges we face with a lunar vehicle. With LEM, like airplanes, we're concerned with cockpit design, pilot vision, life support systems, and all other problems involved in the integration of man and machine. From fabrication to flight test, many of our aircraft lessons apply to LEM. Each lunar excursion module will be built with the same meticulous care and hand craftsmanship that we've devoted to a long line of pioneering experimental aircraft. As we've developed new flight systems, we focus considerable attention on teaching men to operate and maintain them. As a result, we've invested years now in perfecting effective training techniques that will apply to the LEM program. During the past 10 years alone, we've trained over 6,000 pilots, flight engineers, and ground maintenance personnel to fly or maintain aircraft and rockets. The range of experience we will concentrate on the lunar vehicle is as varied as the tests and research projects we've devoted to all areas of flight. Recently, for example, we completed a program to modify the F-106 life support system to accommodate NASA-type pressure suits. This project involved extensive environmental and flight tests with pressure suits and related support equipment, and gave us recent practical experience with life support systems from the standpoint of men as well as equipment. Our prime concern has always been with flight crew safety, and this has governed our philosophy of thorough research and exhaustive testing. In developing an advanced escape system for the F-106, we conducted detailed research of human tolerances, then climaxed intensive ground and air tests by ejecting a man from the aircraft. From such projects, we have gained a first-hand insight into the hard, uncompromising demands of safeguarding life under hostile conditions, and we feel this experience is extremely important to LEM. We are, of course, applying many of our aircraft design lessons to LEM. For instance, we're proposing a docking technique that will be completely familiar to pilots experienced in mid-air refueling. The docking probe we planned for LEM is patterned after the refueling probe we used on the R3Y aerial tanker. In all of our LEM planning, reliability is the key word, the dictating factor. And it's in this vital area, especially, that our airliner experience will pay dividends. Our approach to LEM is that it must be more reliable than any airliner we have ever produced. Our experience with a man in the loop goes beyond airplanes. We're also applying to LEM a great wealth of knowledge and know-how gained in developing and flying the man-rated Atlas. Through Project Mercury and other Atlas space assignments, we know from experience of the painstaking thoroughness demanded for successful space missions. And we also understand the procedures and importance of working closely, harmoniously with others, of blending our men and system into an overall flight team. From rocket development programs, we've also developed other skills vital to LEM. Skills in conducting captive and flight acceptance tests, and in such design areas as flight control and propulsion, plumbing and pressurization. Our diversified experience will be beneficial to LEM, not only from the standpoint of design and reliability, but also through a savings of time and consequently money. For instance, our experience in tethered flight testing with Pogo, the nation's first successful vertical takeoff and landing aircraft. When we subject LEM to the same type of testing, we'll profit from lessons learned in such areas as instrumentation during Pogo tests. Also of value to LEM, the experimental Pogo gave us important experience in the dynamics of four-legged landing gear. It gave us knowledge into such vital areas as visibility, pilot seating configuration, and cockpit displays needed for hovering and transitioning flight. Most importantly, all of our aircraft and rocket experience has been bought and paid for through exhaustive testing and demonstrated success. Now we're focusing it all on the development of the Lunar Excursion Module. In our approach to LEM, we have established as our program goal a series of successful tests, each test supporting and reinforcing the final successful test, the lunar mission. We will apply to LEM an enormous storehouse of knowledge and know-how acquired during the development of other flight vehicles. On one such program, the effects of zero gravity on liquid propellants,
flight components, and instrumentation were studied. On the ground, more specifically at Edwards Rocket Base in California, we are gaining rocket propulsion experience. Here, rocket engines are fired in vacuum, initially created with a steam diffusion system. Our experience with vacuum firings and in the management of similar integrated system tests will aid us immeasurably in light testing of the lunar vehicle. In the area of attitude control, extremely vital for LEM, we're developing a spaceflight simulator, which we will use for the Lunar Excursion Module. The 3-ton, 52-foot-long simulator is mounted on a bearing which floats on friction-free cushion of air. Attitude rockets can maneuver the simulator in the pitch, yaw, and roll axes, allowing us to test attitude control systems under free-floating conditions. Our space research efforts have not been devoted solely to hardware. We are and have been actively engaged in human aspects of space flight, of determining the interface requirements between man and space vehicles. We've been operating the spacecraft simulator called Mars for a year to investigate biomedical, psychological, and engineering problems of manned space flight. It's equipped to simulate an entire space mission from launch to landing. With the simulator, we've developed and tested the working breadboard of a life support system. We're also working on such equipment as an onboard microchemical system, which will permit astronauts to check their physiological chemistry during prolonged confinements.
During the past 3 years, we have invested over $3.25 million of company funds into studies directly related to the lunar mission. This is in addition to government-sponsored research into similar areas. In one of our studies, we used a simulator to investigate lunar landing techniques. The simulator consisted of pilot controls, pilot displays, and an analog computer to represent vehicle dynamics. Test pilots flew the missions. For the pilot controlling pitch and thrust, we concentrated on the landing approach to touchdown phase. We were interested specifically in determining the handling characteristics of the vehicle. In another study that bears on a lunar mission, we investigated the techniques required for rendezvousing and docking two spacecraft. We conducted this research last year to study the components and the techniques needed to accomplish these two critical phases of flight. The test proved the feasibility of our rendezvous and docking procedure and pointed up the need for adequate pilot displays. The seemingly simple matter of visibility, of being able to identify a second vehicle in space, could pose problems during rendezvous and docking. The target vehicle, suspended against a black void and lighted by an intense column beam of light, may not be a recognizable form to the pilot of the approaching vehicle. Instead, it may appear as a light source itself, without a definition. We've been exploring the problems of space visibility and seeking their solutions. On the basis of preliminary experiments, we believe that with small models, we can inexpensively duplicate the same views that an astronaut will have of a second vehicle during rendezvous. With such model simulations, astronauts can be trained on the ground to identify what they are seeing in space. Our studies into this and other space visibility areas are continuing. To determine the effects of a space environment on proposed LEM materials, we sealed specimens for 15 days in a vacuum at 10 to the minus 8 millimeters of mercury. Our purpose was to determine changes, if any, in the optical properties of window materials and to measure the lap shear strength of Scotchwell. The vacuum had no significant detrimental effect on the window materials or the metal bond. In another vacuum test series, we subjected various paint specimens, organic and inorganic, to ultraviolet rays. Since paint is important in regulating the internal temperature of the vehicle, we are determining which type of paint best withstands radiation and vacuum of space. Our radiation research has not been entirely earthbound. In one company-funded project, underway since 1958, we have been using instrumented balloons to make high-altitude radiation measurements. In this continuing research, we are studying solar cosmic rays, especially low-energy gamma rays and high-energy X-rays.
Portions of the Atlas 109D
the rocket used on the Glenn orbital flight, were recovered in South America and Africa and returned to us for analysis. This may look like a magnified picture of a crater on the surface of the moon, but it's actually a pinhead-sized pit on an Atlas skin section caused, we believe, by a micrometeorite. The stainless steel skin sections were dotted with tiny craters, apparently caused by meteorites striking the Atlas in space. Our engineers are studying the miniature craters to determine the size and velocities of the meteorites and to discover, if possible, the physical composition of the particles. For the past 3 years, we've concentrated on studies of meteors and their effects on space vehicles. To simulate meteorite impact, we've employed a variety of techniques, from specially developed meteorite guns to the firing of pellets with explosives. The tests have yielded a wealth of information applicable to LEM. At the Utah Research and Development Center in Salt Lake City, we conducted additional meteorite tests to support our planning for the LEM structure. In the test series, we used samples of metals, insulations, and transparent materials, which we were considering for the lunar vehicle. The tests were conducted in a vacuum environment using 1/8-inch diameter aluminum pellets to simulate the meteorite particles. We've incorporated the test results into the design of the LEM cabin structure and cabin windows.
Our objective in the LEM design was to make the pilot feel at home, even though operating in a hostile environment. A natural transition from aircraft to spacecraft. Crew safety depends primarily on the crew members responding correctly and quickly to given cues. The cues may be exterior or interior, or both. To assure the right responses, visibility, control, and display requirements were integrated. Crew tasks were carefully analyzed. Crew positions were given top priority. Side-by-side seating with the commander on the left and the systems engineer on the right yields optimum communication by sight, sound, and touch. Flight management displays are centered, readily visible by either man. Systems panels are within easy reach. The systems engineer has dual flight controls to provide greater crew safety and greater assurance of mission success. The engineer can take over flight functions instantly if the commander is incapacitated for any reason, such as a meteoroid strike or nausea. At any point in the mission, the crew can jettison the descent stage by flipping this guarded switch. Independently, if any malfunction should occur to the main engine, the commander can jettison the descent stage, shut down the main engine, ignite and bring his standby engines to power, all without removing his hand from the power lever. This capability for rapid positive action is important to crew safety in the hover mode. LEM hovering and landing design considerations were a natural evolution from helicopter and VTO pogo techniques. The main engine control, operated by the left hand, is analogous to the helicopter collective pitch control used for controlling altitude. Attitude control in pitch and roll is accomplished with the attitude control stick held in the right hand and is comparable to a helicopter control stick. Foot pedals, similar to helicopter rudder pedals, provide azimuth control. The arrangement of controls and display panels was developed from studies of normal viewing angles and convenience of reach. Restrictiveness of pressure suits, headgear clearances, restraint harnesses, and access to and from the seated position were considered. A simple probe-drobe technique, already familiar to pilots, was adopted for the docking maneuver. This semi-hard, self-aligning system requires no reorientation of either crew member, their cues, or their controls. Vehicle translation using this reaction engine control makes docking a straightforward operation. The crew has excellent visibility for the initial docking maneuver using the forward windows. Final docking is monitored through the overhead port as the LEM is rotated for final mate with the command module. A probe drogue docking procedure, side-by-side seating, dual flight controls, and a multiple engine configuration were chosen to ensure first-time crew safety and mission success.